Hello everybody and welcome to the second part of our SCoBi Signal of Opportunity Coherent Bistatic Scattering Model tutorial series. In this video we're going to be giving you an example of a GNSS signal traveling through a corn canopy. So the first thing that we're going to do is describe the problem, and we're going to try to visualize certain elements of SCoBi for you to try to get a better feeling for what exactly you're inputting into the simulator whenever you're trying to run one of these sort of problems. We're then going to walk you through inputting values into the vegetation input file, then the configuration input file in Excel. Both of those are in Excel. And finally, we're going to walk you through inputting values into the GUI itself for this simulation. So for this problem, again, we're going to be looking at a GNSS signal. We're going to be looking at agriculture, so we're going to be using one of the agriculture simulations. We're going to have to consider vegetation, which is why we're bolding and italicizing that value. The transmitter orientation is going to be changing. It's going to be variable, so we're going to need to account for that. And our receiver is going to be using the generalized Gaussian antenna input that is included in the GUI. We're going to be using snapshot simulation so we can get a whole bunch of data out of just a little bit of input. And finally, we're going to assume that the soil is just one single layer. So whenever you're creating your vegetation input file, whenever you're trying to describe the scatterers that are affecting your GNSS signal, there are 9 variables that SCoBi requires that you put in order to define those values. And they're all based, or at least we're trying to base them on values that you would obtain while you are recording in-field destructive sampling. Well, obviously not all of them, because the first one that's up is the name of the particle ID. The variable name in here is probably not something that's going to be in your notes, but you get the idea. Next, there's going to be the particle density, or how many objects like this are in a cubic meter. There are 3-dimension values that we'll get to. They are dependent on a couple different things. The begin and end angle, again, I need to try to help visualize that part, so we'll get to that when we get to it. And lastly, the relative permittivity and dielectric loss factor of that value. So the particle ID, while using SCoBi, we consider 4 different inputs that you can use. They are a leaf input, which assumes a geometry of an elliptical disc, and the last 3 all assume that they're cylinders, and they are branches, trees, and needles. So for example, if you're going to be using a leaf, you're going to identify that as L followed by whatever number, and you can have as many of these different kinds as you want. Most likely you're not going to have too terribly many, but you'll have your all your kind of dielectric and size and shape. All those values are going to be assigned to a certain variable, so you can reuse that in different layers. Same goes for all of these different guys right here. So as an example, we are assuming that we have some sort of corn canopy for this problem. And there are going to be 4 different layers. One at the top, which has leaf 1, which has some certain values associated with it. Just think of it as a variable that gets reused in different layers throughout this vegetation layer. So one at layer 1 and one at layer 2. Some kind of branch is placed in the top layer that's different than the one in layer 3. And so on and so forth. So you can kind of mix and match variables between different layers, and all of this is done to try to make it to where you can, you're not necessarily inputting the same values repeatedly over and over. You just define it once and you can place it within the vegetation layer as you please. So next is the density of your variable. So most likely your destructive sampling isn't going to be too terribly different among each of the different, in this case we're looking at corn, so your stalks aren't going to be drastically different in size, hopefully, throughout your field. So we can assume that it will repeat within some amount of area. So to accomplish this, we'll, for example, in this case, I have 5 cylinders, and I'm assuming that at least 5 of these cylinders, whether it's a stalk or a branch or something, at least 5 of them are occurring every cubic meter. So in this case, since there are 5 per cubic meter, my input is going to be 5. Over here, I've got some smaller cylinders, almost this, not quite, but I have 25 of them every 2 cubic meters. So for that, and this is just to show that you can have fractional inputs in SCoBi, for this you would assume that it is 25 over 2 is 12.5 per cubic meter. So you're going to have 12.5 of these particles or scatterers every cubic meter. And that was the second input that you need to consider. The next 3 are the dimensions of your object. So as I mentioned earlier, some are going to be modeled as disks and other as cylinders. If you are using a cylinder, which, as a reminder, includes branches, trees, and needles, there are 3 dimensions that you need to worry about. Dimension 1 and Dimension 2 are actually the same. These are the same value, and we assume that so that we can maintain the size of our matrix for SCoBi. Everything is sort of evenly numbered. So that is the radius of your cylinder. The top and bottom are really, both of these radii are assumed to be the same. And the third one is the height of the cylinder itself, or the length of it. And that does it for that. So the disk is the reason why we needed 3 inputs. If you're using a leaf or something that requires an elliptical disk, your first input needs to be the size of the semi-major axis. The next, the size of the semi-minor axis. And, sorry about that. And finally, the size of the disk itself, or the thickness of the disk. So all 3 of those values are going to define some sort of elliptical shape or circular shape, if so be it. But yeah, that is defining a disk shape. Complex dielectric, I'm sure you guys probably know about this, but certain each element within the corn canopy is going to have a different sort of water content. Water content is the driving factor in describing your relative permittivity. If you have a different kind of medium, we can account for that as well. But for the cases of this, we need to define our complex dielectric, which again is a measurement of the relative permittivity, which measures the decrease in electric field strength relative to a vacuum, and our dielectric loss factor, which is a measure of the electromagnetic energy dissipation. Assuming that you have a sort of crazy material, maybe you could look up those values from a table. From here, you're probably going to be using something to measure them while you're in the field, and you have those on hand. But assuming that you've never heard of this before, you can generally look up this complex dielectric for some sort of material to give a general idea. Whether that's from a EMAG textbook or a microwave remote sensing textbook or something like that. Regardless, you're going to need to put that in to describe the dielectric of whatever scatterer that you're describing. Okay, so those begin and end angles that I mentioned a minute ago. First off, I'd like to thank Alina Koval for this very nice picture that will help explain what a begin and end angle is. Let's back up. We included begin and end angles because we wanted to kind of base these on, again, values that you'd be recording in the field. So if you're out and recording your corn canopy, you're generally going to be describing what angles those the stems are branching off of that corn stalk. So to do that, we're going to take a look at the begin angle, which is the one that's attached closest to that stem. And we're going to assume things are relative to the zenith, the up and down axis, straight up and down. So the angle between the straight up and down axis and wherever that leaf is pointing, that's going to be our first angle. So let's kind of assume that this is something like 30 degrees in this case. I'm not quite sure what it is, but we'll just say that it's 30. So that's going to be our begin angle. Then you're going to be looking at the angle on the opposite side of the leaf, again with respect to the zenith. And you can see that this guy is kind of drooping downwards. So again, we're going to point this along the this up and down axis, the zenith, rotate it all the way down towards the direction that that angle is dipping towards. And that's going to be our end angle. And if we assume that this one's 120, what SCoBi does is it calculates the average between those two angles. So if it was 30 and 120, that's 30 plus 120 is 150 over 2, so it's like 75 degrees. It'll be sitting at some sort of 75 degree angle within a medium of air. And this kind of brings everything together. So you're either going to have a cylinder or a disc that has some dielectric value associated with a cylinder or disc. It's going to be sitting at some angle within that medium. It'll be named and repeated throughout that layer based on that density input that you place. So all of those values together, again, the ID is listed right here at the top. The density, dimensions 1, 2, and 3, your real and imaginary parts of your dielectric, and then your beginning and end angles are all going to be inputs that you place into the vegetation input file. And as you define those 9, well, I guess in this case it's actually 8 parameters, and then 1 value to associate it to a variable, you then can construct a sort of 3-dimensional, I guess you could say, dielectric scatterer, a combined layer. So as you can see here, trunk 1, which actually if you come back and look at it, trunk 1 or T1 is 6 meters in height. That was what our dimension 3 was for a cylinder. And you'll see here that the thickness of our layer was only 4 meters. So what this means is that since it was a 6 meter long trunk within a 4 meter tall layer, that trunk is extending a little bit up into that third layer because it's bigger than what the layer allows. So I just wanted to kind of point that out real quick. But all of these different values, leaf 1, you can kind of see a leaf here in the very most top layer. Branch 4, it's a little bit different than the surrounding layers. All of these define different angles and different scatterers for these values. And I wanted to point out that what SCoBi does essentially is it creates one homogeneous vegetation layer after receiving your inputs. It's not defining, I guess you'd say, volumetric scattering. It's assuming that things are traveling through some sort of homogeneous layer as it travels through the air, vegetation, and ground to compute your coherent scattering for this model. It doesn't have to be this case. We have in the past modeled scattering to account for the diffuse term for your signal, but at the moment we are not including that in the SCoBi package. We wanted to go ahead and get this guy out to the world, and we're going to be working on putting the diffuse term nice and packaged back into it at a later date. But again, I just wanted to point out that this is to define things in a way that is akin to what you're actually seeing in the field, what you're actually recording through destructive sampling. It's not precisely how it's going to be modeled. It's going to incorporate those values, but it is not modeling it in a that sort of 3-dimensional aspect. It's sort of estimating or averaging or computing what that should be in a homogeneous sort of layer. So that does it for this part of the presentation. Next, we're going to be talking about the configuration input file, how you need to insert things into your model from that perspective, followed by we'll talk about the vegetation inputs, then the configuration inputs, and then finally the GUI. Thank you guys so much. I'll see you in just a second. Hey everybody, I'm back and ready to talk about the vegetation input file for our GNSS signal traveling through a corn canopy. So let's get back into our SCoBi download from GitHub, go into the not design folder, let go of that. Let's go back into the source folder, into inputs, and then the vegetation folder to take a look at the default vegetation AGR for agriculture input. So off the bat, we have two sheets for our vegetation input file. We have layers, which defines where the scatterers or where the kinds are within this vegetation medium. And then we have the kind sheet, which describes the scatterers themselves. So the first column is just text that's intended for you. You can change it if you'd like. Just make sure that it's usable and readable to you. SCoBi's not really looking at it. Again, that's all for you to identify what variables you're looking at. So these three columns right here are defining three different scatterers that we're going to be using within our medium. First up is that particle ID that we were talking about. So since this says L1, we're looking at a leaf straight off the bat on that column, which is an elliptical disc. It's a disc scatterer in this case. The other two are branches and trunks, which represent cylinders. The density describes how often that scatter appears per cubic meter throughout the layer itself. So this is going to appear about 38 times per cubic meter, almost 4 times per cubic meter, and 3 times per cubic meter for that particle. The dimensions again correspond to what kind of particle ID you're using. Since this is a leaf, this first value is corresponding to the semi-major axis to our elliptical disc. The second, the semi-minor axis to our elliptical disc, and finally the disc thickness. The other two are computing or taking inputs for the radius of a cylinder right here, and for both of these are for the radius of the cylinder, and the third dimension is the height of the cylinder. EPS-R-real is the real component of your complex dielectric, the relative permittivity portion. The EPS-R imaginary is the imaginary portion of your dielectric. And finally, the begin and end angles, as we depicted earlier, is the angle that your scatter is sitting at. Since both of these are the same, the average of 58 and 58 is 58, so the angle is sitting at a 58 degree angle from the zenith. So that about does it. I guess I'll take a look real quick at the layers. So after we define those, we place them in the included kinds portion of these layers. If we wanted to add more, we could. So this is for us, and we would say that this is 4, and then maybe we just have B1, and that's it. I don't know why maybe you'd have a case like that, but most likely not. But I'm going to get rid of that because that's not part of the problem. But just for information, that's just how that would work if you wanted to add something like that. But as it stands, we're using all 3 of our scatterers within one layer. And that about does it. So once you have this thing set up, save it and get ready to put that into the GUI. Next up, we're going to be looking at the configuration inputs file for our GNSS signal through Core and Canopy. Next, we need to take a look at the configuration inputs file for our simulation setup. So to do this, let's go back into the source folder, into inputs, and into the configuration folder. So since in the problem statement we said that we're looking at a snapshot mode, we're going to look for the SS timestamp for snapshot. It's a single layer ground profile, so we're on the right track here. And we said the transmitter was varying its orientation, so we're going to open this guy up and take a look at it and see what we can interpret about this guy. So we have 4 variables right here along the top row. Again, these are all for you. If you don't like the naming convention of this, you can change it up. This is all for you. Again, don't worry about it. And I guess I should back up real quick and say, again, we have 2 sheets in here. The order of these sheets matter more than the names. You could change the name of this if need be, but do not change the order. SCoBi is looking for the sheet order more than it is any kind of name. So first we'll take a look at the dynamic sheet. So dynamic values are values that are generally changing throughout each simulation, values that are going to be considered to to vary for your simulation type. So again, these values, these names can be changed if you so like, but these are the important guys, those rows beneath those variable titles. And again, order is what really matters here. And that's why it's important to make sure that everything is correct in your GUI, that if you've selected variable transmitter, that you be sure to declare those and place them correctly in your your configuration input file. So again, we said that this was a variable transmitter. So our first two variables that we're defining are the incidence angle of our transmitter and the azimuth angle of our transmitter. So here we have 10, 20, 30, 40, 50, 60, and 70 degrees incidence angles and 15 and 25 degrees azimuth angles. Our RMS height is going to vary by these three values here, 0.5 centimeters, 1 centimeter, and 1.5 centimeters. And the volumetric soil moisture of our ground single layer will vary from 5% up to 40%, as you see right here. So what's important to note about the snapshot mode is that each of these values are being combined together. So you could sort of say for the first run through that we're having 10 combined with 15 combined with 0.5, 0.05, and then perhaps it's 10, 15, 0.5, and then the volumetric soil moisture changes to 10%, and so on and so forth. So within this particular file here, we have, I believe, 7 values right here, 2 in the next column, 3 in the next, and what looks like is 8 in that last one. So that means with these few inputs, we have 336 different combinations that SCoBi is going to calculate for you to take a look at. So this snapshot mode is a very simple way to try to get a lot of data in a compact amount of space. If you're really trying to just examine just a bunch of different configurations, this is a great way to go about doing that. So that's the dynamic sheet, values that are going to be changing throughout your input. Next, we have our ground sheet, which, because this is a single layer soil moisture profile, it's going to be very simple. Again, these titles along each column are there for you. You can change them how you see fit, but the values beneath them are what count. And again, these are pretty simple. So this is sand ratio. So for this problem, we have 0.8, which means 80% of the soil is sand. The clay is what is that? Yeah, 7%. And our bulk density is 1.25 grams per cubic centimeter. And that does it for the vegetation input file. So this is going to be defining, sorry, no, my apologies. The configuration input file, this is defining the transmitter geometry, the RMS height of your soil profile, and other components of your soil profile, such as volumetric soil moisture and the kind of soil that you have. So that does it for the configuration inputs file. We're going to take a look at the GUI itself next. Hey everybody, finally we're going to be taking a look at the GUI portion of the SCoBi input for our corn canopy simulations. We're going to go to source, lib, and then we're going to be running run scobi.m. I currently already have that open over here, so I'm just going to go in MATLAB and hit the run button. And now we're going to be able to choose between our different simulations. So I'm going to pick agriculture because, again, we're looking at corn. And what that's going to do is, again, it's going to load in the default inputs for corn canopies. It's loaded the default agriculture input files, as you can see right there, because that's the default campaign name that it's loaded. Again, we're looking at a snapshot and not a time series simulation. Our ground cover is vegetation, because obviously we're analyzing corn. And we're going to be including the master simulations, but not the attenuation to an Excel file. Those are all up to you. Do as you please with those. Our frequency is the frequency of the good old GPS carrier frequency, 1575.42 megahertz. The distance from the center of the Earth to our transmitter is 26,578 kilometers, and our effective isotropic radiated power is 0 decibels. The polarization of our transmitter is again right-hand circular polarization, and the orientation is changing as we define in our configuration inputs file. The model that we're using to calculate the dielectric of our soil moisture profile is the Dobson model, and again we're assuming that is just one soil layer. It's not multi-layer, as you see right here. Going up here to the receiver inputs, we're assuming again that our receiver is located 20 meters off of the ground with no gain noted for the moment. Our polarization is also right-hand circular polarized, and we're assuming that the antenna is facing the specular point at all moments. Our antenna pattern is a generalized Gaussian. We're just using the basic input for this from the SCoBi GUI itself. And these are values for that: 30 degrees for half our beam width, 30 degrees for our side lobe level, 30 decibels for side lobe level, 25 for our cross polarization level, and we have a value for our antenna pattern at every 1 degree mark. So here is the default input for our configuration input file that we've loaded. Again, it is the snapshot mode, as you see there, single soil moisture layer as denoted there. Our transmitter is varying as we denoted right here, and that's it for the configuration input. Our vegetation again is an agriculture canopy, and we discussed that a minute ago. And once you are done with all that, once you feel comfortable with everything that you see here, feel free to hit that Run SCoBi button, and you should be good to go calculating your power, reflectivity, or whatever you want. So again, thank you guys so much. Be sure to tune into the next video where we talk about P-band signals of opportunity scattering through a forest canopy. Again, thank you guys so much, and feel free to leave a comment or shoot us an email if you are at all confused or need more clarification on something.